Hello and welcome back to the final video in the series. So far we've covered the basics of deep learning in Pytorch and built a model that can tell different music genres apart. But today we're going to solve a slightly more complex problem in a slightly more convoluted way. The task is to recognize speakers, but this time we're taking raw audio files to train an image classifier. Really cool. This will hopefully be a nice introduction to some methods of working with audio and machine learning and getting to fine-tune a pre-trained network. Hope you enjoy. But while we do that, why don't we take a look at the dataset itself. So this is a speaker recognition task. I love how much information people put on their datasets here. You can see a couple examples of code some other people made for this one, well, a while ago. Maybe I should upload mine. But basically there's, I believe, 12 different speakers. Their names are over here, and then we can see what they're saying. In this case, we're doing just we're not doing speech recognition. We're just doing like a speaker like classification. So this column won't mean much for us. And then what it gives us is actually just the path to the WAV file. So if we grab this like as a CSV, we can map the speaker to the file path, or upload the file, change it, and then use the speaker as our label. Cool. It's probably done by now. Oh no, now done. We unzip it, which is also going to take a second. Any questions so far, Gage?
How do we get an image from audio?
That is a very good question, and will be answered very soon. Well, we're going to look at our CSV here from our, make a data frame out of it, and we get to see, again, like the train test splits are kind of already done for us, which is handy. We just need to grab the CSV file for each one. We can see we have an ID for each one, not important. We have the file path, which is super important because we need to grab these files to process them and turn them into images, and then we see the speech in the speaker. And again, we could be doing like a speech recognition task too, like seeing what words they're saying. In this case, we don't need that column at all. So I can double check just to see like what's the distribution of our classes, which is super important. We have a lot of these guys up front, and then not quite so much for the last few here. This could be a problem, but we're gonna see when we test it out how well our model performs. So now we have a couple of this is like the first of a number of things that make this task actually very difficult, and we'll get to see how well the network performs on it. So again, I'm just turning all of these labels into values. So we make a list of the speakers, and then for each speaker we see in the actual data frame, we switch it to the index of that one. So it'll just be 0 through 12, I think, or 15 different 17, I lied. And then I'm gonna go ahead and see, just make sure that things line up as we'd expect, and we have things in the right order. For this WAV file, we have this speaker, and they're all numbers now, which is nice to see, because again, we can't process words raw as in this case with this type of network. So I kind of already set the max length. This is just to make sure. I believe the files get a little bit longer. Now that I realize, I love this for myself to not have to run this code, because I just did this loop to see how long it was, set the max length. So this is going to be about 7 seconds for the longest WAV file, which is important for us to know because we're going to need to do padding. If not, let's say like we were talking about when we put into the network, we have to put like a constant, like an actual value for the number of input features, right? If one file has just like say like 3 seconds, and then the longest file has 7 seconds, how are we going to handle that? How do we make sure that we get all the input values that we'd expect? And that's going to be padding, which is not complicated to do, but it's important to note, otherwise we're going to get a lot of errors. And this actually takes a while. Please, oh no, not letting me stop. I'll just restart the whole runtime. I'm not going to do that because you'd have to download the dataset again, probably. Cool. So this is just me grabbing. This is just a way to get through, again, pandas likes things in columns. To grab things from like a row, you kind of have to do like a function like this. So 0 is just the first column, and this is the row 1. I think it might be backwards, but when we do torch.audio, torch audio load, we get both the waveform and the sample rate. And when we play back audio, we need to know both to play it back properly.
His newborn cunning gave him poise and control.
So that's our phrase for this one. Let me double check. I believe it should be row first. Yeah.
His immaculate appearance was gone.
So we have both male and female speakers. If we want, we could change this into like a binary classification problem, if assuming we had as many like female speakers as male speakers. We can go ahead and see if you're just curious. So this one is mono. They're all mono. So that's again why it's 1 by this many samples. But again, notice that it's not going to be the same if I load a different one right here. So they're all of different length, which means I can't put this into my network consistently. So what we're going to do is we're just going to pad them, and we just make a tensor of zeros based on the max length value, which we already have set. And we just add that to, in this case, just one waveform. So now it's always going to be this long. We don't need the extra dimension. So this is just so we can see with one example. So from the wave file we just loaded, this is like a lot to do. Same thing. There's a lot of resizing we have to do as well. So this is just an example of what we need to do, but for every single sample we get. So to get the mouse spectrogram, Torch Audio just has a transform for that, and we use the transform because that works well when we use a custom dataset class, and we'll talk about that more later. We do want to normalize things like we talked about before. We make the spectrogram based on this like again, this right here is just a transform, and then to make the actual spectrogram we want, we have to put in the waveform that we pulled out here. Making sense so far?
Yep.
Okay, cool. And then the CMAP is just a color map. The network that we're going to use that's pre-trained is expecting RGB values. And when you do like a regular mouse spectrogram, it's in black and white. So I wanted to add color to it, and we just make this map. You can choose whatever you want. Like this is just one of my favorite color maps. So it's going to be like blue and yellow, I think. And then we plot it out. So go ahead and just plot it first. So we see our little waveform, and we plot two things. So first we have the audio file as it is. And then we need to reshape it to, again, we're using a pre-trained network, which expects not only everything to be the same size, but of a certain size. So it needs to be 224 by 224. So again, we pull up transforms, and now we're transforming, like this is an image transform from this long image to one that's square in 224 by 224. And I feel like it goes without saying, usually when you resize an image, you get you lose some information. Let's say, especially if there's information like diagonally, everything's getting kind of like squished together, even though this one it's not even square to begin with. So this is yet another problem. I wanted to just take note as we go. We have issue number 1, which is like the data distribution isn't like ideal. It's not terrible, it's not ideal. Issue number 2 is to get all of these spectrograms that we want into the correct size. We're losing some information. Things get distorted as we do, and as you can see, there's actually not like a lot super visible here. So this is just like annoying. You have to do like a lot of like finding the right dimension, changing it, and then put it into the right format. So I need to make this a tensor from the NumPy version, which is what we get from the RGB image when we do CMAP. So it's from NumPy and then to a torch tensor, so I can see the shape. And then I'm moving the dimensions around and adding a dimension so that I can resize it, because it has to be a certain like dimension for the resize to work as I'd like. It's kind of annoying. I like unsqueeze and then squeeze it back. There's probably somebody knows like a more efficient way to do all of this. If you happen to know in the comments, like please, the next time I want to do this, I'd like it to not go through so much trouble. But this was my way of getting it happy. When you move between like just PyTorch in general, but like from NumPy and then to PyTorch, things are technically like in different formats, and things, every function's expecting things to be, the dimensions to be in a certain order or a certain number of dimensions. So sometimes you have to do a little bit of this like wiggle work. Anyway, so this is our original image with the full time, and then this is our image. This is with the pad, right? So you'll notice to the right, there's no information here. This is how long the actual WAV file was before. Then we padded it, and then we made an image of it, so it's now super long. And then we resized it in this like squished version right here. So double checking the sample rate, which should still be 60,000. We can check the shape again, same as before. I really don't need these. And then I'm gonna change just to see, like you can change the color map. And this, I think this was just my favorite. And this is, again, a spectrogram. I feel like everyone's already familiar with what that is, right? So the color is the magnitude, the frequency is the y-axis, and then time is the x-axis, which is why, again, this is cut off to the right. Cool. So this is a custom dataset class. So just like before, we would import dataset. And before, I think for the first one, we just did like a tensor dataset. We had 2 tensors that we used to define the class. And what it's doing internally is kind of making one of these, like something that is of the dataset class. And when it gets an item, it just returns the inputs and the targets, which is just going to be tensors. But what we have from our CSV file is not tensors. The function that we're implementing getItem is just what gets called when we run through a loader, like the train loader or the test loader. The index is what we get going into this function. So it'll just send a list of indices, which may be shuffled. So to find that, well, I should say, to make the speech dataset class, we're going to take our, we need a data frame for it to read from. So we're gonna walk through these. I'm gonna set this up. We're gonna walk through these first, just so the data set's there. And this is us sending our data frames in. So we have one data frame for the test CSV, and we have one data frame for the trained data set, which we read that one like way up on top. And then we do have a transform. The transform, and I probably should have like moved it down here, are the 3 things that we need to do. We need to once we have the audio file, you need to take the audio file and make it into a MEL spectrogram. So we have an image. Then the second step is to resize it into the right size. And then the last step is to make it into a tensor. But there's one thing missing from what we did up top, which is changing the color, because we need an RGB image. So even after we do this transform, there's going to be a couple more steps inside of our dataset class. Is this making more or less sense so far? And sorry, I put things in a weird order here.
No, it makes sense.
Cool. So when we grab an item, this is us going from, again, we just have the data frame, and the data frame just has the file path and the speaker. So from the data frame, at that index, 0 is just going to be the file path. I'm going to grab that file path and use Torch Audio to load that file path. And then I unsqueeze the extra dimension. I add my padding to make sure everything's the right size going in. And then, or the same size, I should say. Then we do our transform, which is always going to be true, but I just have this here. So I make the MEL spectrogram. I do the resize. And I didn't pass this in. I could have just done that's why. Okay. Now I remember. So the reason we can't do the reason that this one doesn't work, the reason that it's just kind of hanging around, and I leave transform equals true, I should just like remove this and then have it always run this, but okay. This is my scatterbrain. The reason that this doesn't work is because it's not going to be an RGB image at the end. And there's probably, I wouldn't be surprised if Torch Vision has some transform for that. I didn't see one, so I just kind of manually did each of these things. So I do make the MEL spectrogram, then I do the color map before, I do the like weird resizing thing to get things into the right dimensions. Make sure that there aren't any extra dimensions, and then now that I have my from the file path, I've gotten the image that's the right size and has RGB values. That's going to be my input. And then my target is still just, I'm looking at the data frame, and now I'm looking at the other column, which is the speaker. So based on the input of this entire image, every pixel in their RGB value, your goal is to find this target, which is the label. Do this one classification task. Cool. Making sense so far?
Yeah.
And this is how you would make a custom dataset class. This is I don't even think you need to implement this, to be honest, but you do have to implement get item, and sometimes it's as simple as literally just like inputs and targets based on the index of however you saved your information. Just grab the inputs and targets from that. But in this case, we have to do a lot of transformation to our data. Cool. So again, I'm changing for the test data frame, because now we have a different data frame for the test CSV. We're just, again, changing those labels, like categorical labels, into numerical values. Then we make our train loader and test loader from our train and test dataset, which come from our dataset class, our custom dataset we made. And then this is super important, we do need to know how many classes we have. So this is just the length of our, like, the unique names and unique labels in our speaker column. Because we have the number of classes, we can now update this model. So this is really, really cool. So VGG19, if I'm not mistaken, is trained on like ImageNet. So it's like thousands of thousands of images of just like stuff, all kinds of things. There's images of cats, images of objects, images of trees or whatever. And the network was trained to do classification on all of these things. So what it's learned now is how to pick up features. It's learned how to pick up like curves, how to pick up different colors. It's recognizing patterns, it's recognizing shapes as maybe like a tail. And again, like these are super abstracted, so it's never gonna, like inside the network, it's never thinking, oh, this is a tail, and it's not gonna completely exactly map to a tail. It's just the combination of the features of let's say like one layer is picking up let's talk about this cat here, right? So one right, so like one layer is picking up like the pattern of, oh, there's something circular, right? And then something else is picking up the patterns of, oh, it's furry. And then the combination of those features of, oh, it's round and it's furry and it has 2 ears. Again, it doesn't know it has 2 ears until it's picked up the feature of, hey, there's like a point here, and then there's like 2 of them that are so far apart on this bigger circle. With all those features combined, it's learned to classify, okay, that's a cat. But the important thing is that to do that, like I was saying, it has to pick up features at the layers before it does that classification. So that means when it takes up any image, it's already trained to pick up important features like curves, important features like things that may or may not look or resemble tails, or may or may not resemble feet or what have you. So this is why the network it's so powerful, and we can use it for new tasks now. But how do we do that, right? This was trained to say, I don't know how many classes originally, and we can actually check real quick. So if we go to the next line, this is the beauty of being able to just like print the model definition. I can see exactly what it's made out of. And of course it's working with images, so we'll see a lot of like convolutional layers, see our activation functions, and blah 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 blah. This is actually really cool too, because we can see it's segmented into parts, and then we see our final few layers, which are the classifier part, right? And I know now that VGG19 was trained to classify between 1,000 different classes, 1,000 different things. Maybe it's 1,000 different animals or what have you. I'm actually not sure. But for our problem, we don't need all of those classes, right? And if we keep the network exactly as it is, it's just going to classify between those objects. And we're going to be introducing something new, which is a spectrogram, right? So what I'm going to do to fine-tune this pre-trained network is I'm just going to take off this last classification layer, and I'm going to replace it with one that has the number of classes that I need. And these, like this new layer, hasn't been trained. Like it doesn't even know what those features, like what those classes attend to. But the network already has this layer right before the output layer that is super dense with information about what features it has, right? And these are the most like abstracted features, because we've gone through like the details of, hey, this group of pixels might be like a little triangle, and this group of features might be like, oh, like the head of a cat, like it has like 2 points and has this, and then something more vague of, hey, this is like a cat, and maybe there's like a chair over here or something, right? Really weird example, but the idea is like it's gotten all the information it needs, like very compressed into these little vectors that have a ton of meaning about what is in the image. And now all I'm doing is replacing this last layer with saying, okay, I see with my little eye something that has these features here. What is it? Out of these are your 10 options to pick from. Instead of 1,000 options or like an infinite number of options, it has these 10 classes to pick from. And what's going to slowly learn is, oh, when I have this feature and this feature and this feature, it's probably this speaker. When I have this feature and this feature and this feature, like really showing up and not the others, then it's probably the speaker, right? But the idea is that it already can find those features in an image. Cool. Perhaps that was too detailed an explanation, but making sense?
Yeah, that makes sense for now.
So again, this is the whole model. I'm gonna take the model dot classifier, which is this section right here, at 6, and it very handy. It tells me what it is. I'm just gonna replace it with my own linear layer, and it has to have the same number of input features because I mean, like it's taking in whatever came out of the last layer. And then it's going to output to the number of classes I have, which is why it's super important just to grab the num classes up here. Cool. So replace that one last layer in my pre-trained network. And I should also say, when you pull it, it's valuable to put pre-trained equals true. That loads the weights that already exist for the network that was already trained to classify between these 1,000 classes. If we made pre-trained equals false, everything I just said about it being able to pick out features is completely wrong. It's like a blanket initialization with basically like random values for all of the weights. So actually, we might run this. I'm going to run it once, and then I'm going to run it once with pre-trained equals false just so we can see how that turns out. And then the training loop looks, again, like exactly the same as before. We're doing a classification task, so it's cost entropy loss. I don't know why I left it at 5 epochs. I know this takes a little bit longer to do. Like it's doing a lot of computation when it just like loads stuff out of the data set. I am on GPU, I believe. So we're gonna see if it takes too long. Oh yeah, it's gonna take a while. So how confident would you feel if I, like, let's say right now I just assigned you. I'm not going to, because you do whatever you want, but like I picked out a data set from Kaggle right now, and I said, hey, I want you to train a classifier for this data set. How confident are you? Good.
I think with enough reading documentation and figuring stuff out, I could figure it out because I know the why of each step more so than I did, a semester ago.
Yeah, that's cool.
Yeah.
How do you feel about how long did we spend? That was 2 hours. Not bad. I feel like it was worth it for 2 hours.
Yeah, I think so. That's better than some of my lectures at college.
All right, that's good to hear. So I just wanted to say before I wrap up, a big thank you to Gage. Like, we're still waiting for it to train right now, but I'll show you the output at the end. Maybe give a quick conclusion. But super big thanks for tagging along. It's nice to, like, as I'm explaining stuff, and I know like most of my videos in my audience, like, it's really just music so far and maybe a little bit of programming. It's nice to sort of like introduce myself to another like pool of content and have somebody that I know fits my audience that may or may not be super familiar with this stuff also find interest in this and help, like, I guess, the audience out as well as we learn together. Of course, again, I'm not a super expert in this field or anything. I'm just showing what I know because I know if I'm interested in this and also like a music person, I know I'm not the only one. And if I can show you how to do one or two simple things, maybe I'm not the most knowledgeable, maybe I'm not the most accurate on all of the facts. If I can give you a head start into doing that, just something that I would have appreciated like a ton myself, I feel like I'm doing something of service. So I really appreciate Gage and helping me out on this. Any want to say a quick goodbye or any other notes to YouTube real quick before you sign off, Gage?
Uh, Never stop learning. Sounds cliche, but like, actually,
Sounds good. So I think that's a fair way to end
this
it.
has been really nice. Yeah, thanks for doing this.
Thank you for tagging along. I should say. We'll call it there.